Hi everyone, hope everyone is doing well. Today I'm going to run through a subtopic of an even bigger topic. The bigger topic being electrostatics and the subtopic being Coulombs law in 2-dimension. Now it's important for us to remember what Coulombs law, be able to state it in words, and more importantly, to use it. Now, if you're going to state Coulombs law, then you must state it like this. It is the magnitude. By magnitude, we mean size, we mean amount, we mean quantity, we mean the value. The magnitude of the electrostatic force exerted by one charge on another is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between their centers. That's Coulombs law in words. You can also write it in terms of an equation where you say F, which is the force of concern, is K, which is Coulomb's constant. Then you say Q1, the charge on object 1, multiplied by Q2, the product, Q1, Q2, divided by R squared, which is the distance between their centers. It is good to know then that this particular law is applicable on a one-dimensional situation when all the charges are on the same straight line. For an example, you could have a positively charged object here with a magnitude of Q1, and then another positively charged object here with the magnitude of Q2. Then the distance between their centers here, and that's R as it were. Coulomb's law is applicable in this situation where all the objects, charged spheres, if you may, are on the same straight line. What if they're not? What if the charged spheres are not on the same straight line? What if I've got a sphere charged here is negative? We call it Q3. And maybe another one here, it's negative. We call it Q1. And another one there, it's also negative. We call it Q2. This is a two-dimensional diagram. The spheres or the objects are not on the same straight line. So how do we apply Coulomb's law in such a situation when the objects, charged spheres, are not on the same straight line? What's important in all of this is to be able to draw a force diagram, or if you like, you may call it a free body diagram. Now we need to understand what type of forces exist, whether they are attractive forces or repulsive forces. Let's say, for an example, we want to know the net force, right, acting on object Q1. So we want to know the net force that's acting on this particular object Q1 due to Q3, which I see there, and Q2, which I also see there. Fine, it's possible to get this right. Now, if you consider the force that Q3 exerts on Q1, that type of force is repulsive. The force that Q3 exerts on Q1. So let's look at it this way. So this will be your Q3, all right? And this will be your Q1. What is Q3 doing to Q1? Q3 is repelling Q1. Q3 is pushing Q1 away from itself. So the force direction of the force that Q3 exerts on Q1 is a downward direction. So you can say it's going to the south if you want. So the force that Q3 exerts on Q1, so what is Q3 doing again? Just think about it. Q3 is pushing Q1 away from itself. So we must be clear on the direction. So let's see this. So this is my free body diagram. I'll put my dot representing my Q1, and then I'm looking for the direction of the force that Q3 exerts on Q1. So this one will be in this particular direction. So I'm seeing it. It's force Q3 on Q1. So I've got that direction. But the forces don't only stop with what Q3 does to Q1. There's also the force that Q2 is exerting on Q1. That force is repulsive. Both charges are like charges. So let's look at this. This is Q1, and this is Q2. So what is Q2 doing to Q1? Q2 is pushing Q1 away from itself. So in other words, if I was to draw this, I would say it moves to the left. What is Q2 doing again? Q2 is repelling Q1. So the direction of the force would be like this. So this would be the force that Q2 exerts on Q1. So it's important to know that, because with this kind of diagram in mind, it becomes easier to calculate the net force on Q1 due to the presence of Q3 as well as Q2. Now, since force is a vector, we must consider how to actually evaluate or solve for vectors in such a case. So in this case, the resultant force becomes the diagonal right here. All right, so the F net becomes the diagonal right there, and we finish up our diagram with some dotted lines in this particular case. So it's important then to know that once you've got this type of diagram, then you can be able from there on to calculate the net force. Since force is a vector and we're solving it using vector methods, then it means that we need to manipulate and use Pythagoras theorem. What are we looking for? We're looking for the net force. So what do we have? So obviously there's force Q2 on Q1 right at the top right there. And then I could also write it in the same manner here as force Q2 on Q1, meaning to me that the net force, and I'm doing Pythagoras theorem, the net force squared would be equal to force Q3 on Q1, that type of force squared, plus force Q2 on Q1, and also this one will be squared. Obviously, when you have gotten your numbers into square root and be able to get that type of force. So at the end of the day, when you think about it, it now becomes net force, and I'm just going to write this here, is the root of force Q3 on Q1 and it's squared, plus force Q2 on Q1, and again also it is squared. Now that's how you get the magnitude of that force, and in this case it's Coulombs law in two-dimensional. But let's add some more flavor into all of this. It's important then that if the question asks you calculate the net force acting on Q1 due to the presence of Q2 and Q3, you should show the magnitude, but also the direction. Let's say you're given cardinal points, okay? You're given cardinal points. So what's that? You're given your north, your east, your west, and your south. And what you're asked to do is to calculate the net force, and you have, and now you need to give direction as well. Now we employ trigonometry. So the angle that we're looking for is the angle that the F net is acting upon or on. So this angle here, theta, let's call it theta. Using trigonometry, we can say to ourselves, I've got this side, and this side is the opposite side. And then I've got this side, and this side is the adjacent side. So I'll just put my 90 degrees just to refresh your memory. So therefore, I'm going to say to myself, tan theta is equal to opposite, because that's what works. I have opposite, I have adjacent, tan would come handy. So tan theta is equal to opposite force Q3 on Q1 divided by the particular adjacent force Q2 on Q1. And that just becomes how you get your direction. And in this case, cardinal points, that's the north, that's the west, that's the east, and that's the south. Considering this particular F net and how it is looking like, I think for me, it would be safe to say this is southwest. So you'll get your angle, then you say southwest, considering that you have your F net. All right, so that's just the theory part of it. Maybe Let's try to do a question to make sure that we understand what we are talking about. Coulombs law in a two-dimensional situation. All right, so we'll try to do a past exam paper just to make sure that every one of us gets what's going on here. So here's a typical question that we can do together as a team. All right, so let's do it together. Here you guys can hear me, which is great, by the way. Now, let me just share the screen. Move a bit quick. There it is. 2019 Mpumalanga Prelim Paper 1, question 7. I must acknowledge that. Here's the question. 3 charged spheres, X, Y, and Z, are placed perpendicular to each other as shown in the diagram below. So there's your diagram there. You've got a two-dimensional situation. Then the first question obviously says, state Coulombs law. I think that's what I started off with. So again, guys, it's important to know these definitions. It's either you're going to get 2 marks or you're going to get 0 marks. There's no in between. So we now know how to state Coulombs law. But then we go to 7.2, which is probably the interesting one in this particular case. It says, draw a labeled vector diagram to show the directions of the electrostatic forces and the net force that the charged sphere Y experiences due to the presence of charged spheres X and Z respectively. All right, let's get down to business. Let's see what we're doing. First things first, the force or the vector diagram there. Okay, so the force is being felt by the sphere Y. So let me just put Y as a dot, maybe somewhere there, just to make sure that it's clear. So now we see this. Z is negatively charged. Y is negatively charged. So which means to me that Z exerts a repulsive force on Y. Z is pushing Y away from him. So Z is saying, Y, move away from me. And in that direction, we're saying that the force that Z exerts on Y is to the left, away from Z. So the force that Z exerts on Y is to the left, or if you like, you can call it to the west. Let's see what X, which is positively charged, is doing to Y. So between a positively charged sphere and a negatively charged sphere, the type of force that exists is an attractive force. So in such a scenario, we're looking at an attractive force. What is X doing to Y? X is attracting Y. What is X doing to Y? X says, Y, come towards me. I'm attracting you towards me. It's an attractive force. So this type of force is this one that goes just down this way, and then it's the force that that X exerts on Y. But let's read the question again. It says, and it's in capital letters, the net force that the charge Y experiences. So now we need to write the net force. We say to ourselves, the net force is the diagonal in this case, and I'll write it like this. This will be the direction of the net force. So that becomes our 7.2, and this question is usually about 2 marks, maybe 3 in the exam in this case, since we're writing the F net as well. Maybe you can get a mark for this. That would be a 1 mark, and your 1 mark there, and maybe your 3rd mark would be that one right there. Fine. So that's what we have for the vector diagram. But I want to go further now. I want to make sure that we get what's going on. Now we need to do maybe a simple calculation on all of this. Then it continues, 7.3. Calculate the magnitude of the net force experienced by sphere Y due to the presence of X and Z. And that's a good 5 marks. They just said calculate the magnitude. So we note the question, magnitude of the net force. Our free body diagram, again, looks something like this. So that's the force that Z exerts on Y, and down here is the force that X exerts on Y. And we know that the resultant force or the net force is this one here, which is F net, as you can see. Now, we need to do some mathematics here. As a formula, you will know that force, K, is equal to K and then Q1, Q2 over R squared. Please always write this because you get a mark for writing a formula. We need to get the force that Z exerts on Y. We need to get the force that Z exerts on Y. Now we need to remember the charges that were there previously. So maybe we can revisit that one day and see if we can get the charges that were there previously. So you must keep this in mind, that you must remember the charge that X had, the charge that Z had as well. I'm trying to move here so that you can see what I'm talking about here. So there you are, the charges that Z had, the charges that X had, and the charges that Y has as well. So let's just write it here just to make sure that everything is fine. Remember, we're looking for the force, the magnitude of the force. We've already written our formula. That's probably our first mark. Let's get the force that Z exerts on Y. Formula K, that's Coulomb's constant, 9 by 10 to the power 9. And then I've got the magnitude, 6 microcoulombs. Micro means by 10 to the power negative 6, multiplied by, again, the magnitude there, 2 by 10 to the power negative 6. All this over R squared, which is measured in meters here, which is 0.3, and that's squared, which gives me 1.2 newtons. And judging by our diagram, we said our diagram, just as a reminder again, it's like this. So it's the force Z on Y and the force X on Y. This one is to the left. So it's the type of force to the left. So we can get the one done by X on Y. Force X on Y would be, again, 9 by 10 to the power 9 multiplied by the individual charges there. So I've got the 6 by 10 to the power negative 6 again, and that again 2.5 by 10 to the power negative 6. All of this divided by the distance between them, 0.4 squared. At the end of the day, I've got 0.844 newtons, and this one will be down. If we're using cardinal points, we'd say south. Now we're looking for our net force. There we are, our net force. Judging by what I taught in the beginning, I said the net force would be equal to the root of the force X on Y squared plus force Z on Y, and also that one is squared. And then we can have it now in this case as root of 0.844, that's force X on Y squared, plus Z on Y, 1.2 squared. It's a lot of math, but we can get it right, and it's 1.47 newtons. Now, notice that I'll stop here on this question because I was just asked to calculate the magnitude. So the wording of the question is very important. What if they ask me to just calculate the force? Then that means that I need to consider the magnitude as well as the direction. Maybe let's do a question like that, right? That considers magnitude as well as direction. That would be very interesting to consider magnitude as well as direction. So that's our first one right there. Let me try and see if I can try and do another question with you as we learn more and more. So it's important to then continually remember what to do when dealing with Coulombs law. Here's another question here that we can do. And it's a 2016 Metro North Prelim, paper 1, and it's question number 7. 3 charged spheres, Q1, Q2, and Q3, getting charges respectively of those values that you're looking at, are positioned as shown in the diagram below. So there's our diagram. That's fine. 7.1, the usual state Coulombs law. And I'm okay with that. And I hope that you're okay with that. We must learn. 7.2, calculate the number of excess electrons on Q2. Calculate the number of excess electrons on Q2. All right, let's think. I'm looking for the number of excess electrons, the charge on Q2, as you can see for yourself, is -2 times 10 to the power -4. And that's the total charge. That's the magnitude of the charge. But I'm looking for the excess electrons. As always, your choice of an equation always depends on the information given. So whatever equation you choose depends on the info that you've been given. The charge on Q2, -2 by 10 to the power -4, is equal to N, which is the number of electrons that are in excess, which I don't know, which are what I'm looking for, multiplied by the charge QE of 1 electron, which is -1,6 by 10 to the power -19. Then now you can divide and divide -2 by 10 to the power -4 divided by -1,6 by 10 to the power -19. As an answer, you will get it to the point of 1,25 times 10 to the power 15 electrons. So this will be the number of electrons available in excess, which ultimately give us that particular charge of, or rather the charge on Q2 as -2 times 10 to the power -4. But yeah, that's part of the question. But what are we looking for? What are we interested in? We're interested in calculating Coulombs law. That's what we're interested in. Here's our question. Calculate the net electrostatic force exerted on charge Q1 by charges Q2 and Q3. 6 marks. So they didn't say the magnitude, they just said net electrostatic force. I need to include the direction, the angle, as well as the magnitude. All right, so just remind ourselves of where we're coming from in this particular question. So here's where we're coming from, and that's good to go. So we were saying to ourselves, we need to have a force diagram, all right, or a free body diagram. I like to put it better off that way. Free body diagram. Let's notice Q3 positively charged, Q1 positively charged, right? And then maybe Q2 negatively charged. We need to get the direction of the forces exerted. What is Q3 doing to Q1, pushing it away from itself? So I can have it this way. That's my Q1. What is Q3 doing to Q1? Away. So force Q3 on Q1. And then maybe we can have it this way. What is Q1, or what is Q2 doing to Q1? So this one is positive and this one is negative. So definitely Q2 is attracting Q1. So it's the direction to the right, or we can say to the east, because they gave us the cardinal point. So force Q2 on Q1. As always, your free body diagram has your diagonal as your F net in this particular case. Finish it up nicely with the dotted line. Excuse the bad handwriting. Finish it up with the dotted line. So we can just stretch it up nicely to make it look a bit neater. There you are. Let me just take that out a bit. And then we can stretch it up to this particular level. There we are. So that's the F net. Good. Let's do the calculations. What's our first mark? The formula. Our first mark is the formula. What's that one? F is equal to K Q1 Q2, all this over R squared. Let's get the force that Q2 exerts on Q1. So I'm looking for the force F that maybe Q2 exerts on Q1. So what's that one there? It's going to be 9 by 10 to the power 9 multiplied by 2 times 10 to the power -5. That's Q2 on Q1 times again 2 times 10 to the power -4. The ultimate distance between their centers being 0,5 meters, and that's squared. I must state that it's important to remember that distance must be in meters rather. And if distance is in meters, then it's easy, you can just plug it in. If it's in centimeters, remember to divide by 100. If it's in millimeters, remember to divide by 1,000. So 144 newtons. And what direction is this for me? East. So that's east right there. I need the force that Q3 exerts on Q1. It's going to be now 9 by 10 to the power 9 multiplied, and then I'm good to go, by 2 times 10 to the power negative 5 times 2 times 10 to the power negative 4. The distance this time is 0.4, and that one is squared, all right? And then FQ3 on Q1 ultimately becomes 225, and that's newtons. And let's see what direction is that. Definitely that is south, like what you're looking at. Okay, so now I know the forces. The rest is just math, and I'm applying Pythagoras theorem. All right, so please keep that in mind. We're now applying Pythagoras theorem just to make sure that we get the F net as they wanted us to get it. So you have this, guys, you can see this. Just want to erase this a bit so I can have a bit of some space to write this on, so that everyone can see what's going on. Now I'm looking for the force that is exerted on that particular charge. A reminder, it's always easier to do this while looking at the free body diagram right there. Okay, who's this? FQ2 on Q1. Who's this? FQ3 on Q1. Looking for F net, this diagonal here. Finished up nicely there, finished up nicely. F net, let's do it then. It's now going to be for me root of what? I remember we got 144. That was FQ2 on Q1, and it must be squared. Then another one, FQ3 on Q1, which for me now is 225. And again, it must be squared. Do your maths properly. 267.13 newtons. Judging by the question, they said calculate the F net. Now I would need to be able to get the angle. Let's break it down. So here is your theta, that angle that I talked about. This is your F net there. We want to know at what angle is this particular F net acting upon. Let's see what we have. We've got opposite again. Let's see what we have. We've got adjacent, which is this particular part there. So what do we say? Remember, FQ3 on Q1 right there was my 225 newtons that I calculated. And FQ2 on Q1, and I just want to put it here, was my 144 newtons. So then to finish this up, tan theta is opposite 225 over adjacent, which is 144. Then when you do your maths now, theta is shift of tan, calculated definitely 225 over 144. Mathematically, the answer becomes 57.38 degrees. Now, at the end of the day, the F net, now you're putting it the final one, what's the magnitude? 267.13 newtons. What's the angle? 57.38 degrees. In what direction? Let's look at it. In what direction here? Look at that. Show something like this. So it's southeast, right? So we can write it as like southeast, S-E, S-E. So basically, that's what you do when you're doing Coulombs law. Obviously, they'll come in different formats and different ways and stuff like that. Either way, what you're supposed to know is how to be able to do Coulombs law. So I suggest that we work extremely hard. We do our best. We keep pushing. We don't give up. We nail these exams that are coming up. We work extremely hard. I can't overemphasize that one. I wish you all the best for your exams as they are pending and coming close. I'll see you again on another new video that I'm going to be doing soon. Take care always.